So, welcome everyone, and thank you for joining us virtually for the latest version of the Variant Effect seminar series. My name is Jan. I'm a member of the VEST organizing committee, along with Adrini de Souza, Diego Calderon, Ohana Bezeres, and Mariano Martin. These seminars are made possible with support and a lot of help from Lara Muffley and Alex Hopkins, among several others, and our sponsors, the Atlas of Variant Effect Alliance. As a reminder, we're always on the lookout for potential speakers for future seminars. If there is anyone you would like to see present, or if you're interested in sharing some of your own work, then feel free to submit a speaker nomination form. As usual, before starting the presentation, I have a few housekeeping items to mention. Each talk is around 20 to 25 minutes, but there should be time for a few questions. Please pose those questions at any time to the Zoom Q&A, and we'll read them out to the speaker at the end. If you have additional questions after the end of the seminar and you're an AVE member, feel free to visit our seminar series Slack channel for more discussion. And finally, we are posting updates to our Twitter account, so be sure to follow us there. You can catch today's seminar and previous presentation that have been recorded on our affiliate CMAP YouTube channel. All details of this seminar series can be found on our website, including a regularly updated schedule of upcoming speakers. For the last housekeeping item, and this is rarely an issue, but as a reminder, please be considerate when posting comments or questions. We expect everyone to be respectful and use welcoming and inclusive language. Today, we have two great presentations. The first one from Dr. Benjamin Livesley. He's a postdoc researcher currently working at the Institute of Genetics and Cancer at the University of Edinburgh. Over the course of his PhD and postdoc, Ben has worked towards finding an unbiased method to assess the performance of computational variant effect predictors. Ben, without further ado, whenever you're ready.
All right, let's hope the screen share goes as well as it did in the practice. All right, is this looking good?
It's a bit fuzzy, or is it just me? Ah, now it's clear. Okay, perfect.
Okay, good. Might have just been a buffering issue. Okay, so good afternoon or morning, everyone. I'm Ben Livesley, and I'm a postdoctoral researcher in the lab of Professor Joe Marsh at the Institute of Genetics and Cancer in Edinburgh. I'm here today to talk about our ongoing project to benchmark computational methods for predicting variant effects using datasets that are derived from deep mutational scanning studies. So let's start with some background on variant effect predictors. Variant effect predictors, or VEPs, are software that attempts to predict the likelihood or the severity of a given protein or gene level variant on fitness. I imagine that many of you here today are aware of predictors like SIFT and polyphen2, but computational prediction of variant effect is a really fast-moving field, and multiple new VEPs based on cutting-edge technology are being released each year. So this is a fairly quickly constructed illustration to show how the release of new VEPs has accelerated.
Oh, looks like
what just happened?
You stopped sharing, I think, or the sharing stopped.
It said reconnecting for some reason, but I will reshare. Okay, are we back up again?
Yes.
Yeah, so with such a large number of VEPs to choose from, how can we compare them in a fair manner to select which is the best or the most useful? VEP benchmarking has been around as long as VEPs themselves have. After all, if you've just come up with some novel technique for predicting variant fitness, you'll want to demonstrate how well it works. The predominant methodology in early benchmarks has been to compile a series of high confidence pathogenic variants and high confidence benign variants, and then use them to assess the performance of your predictor as well as several others. So this 2015 paper by Grimm et al., the evaluation of tools used to predict the impact of missense variants is hindered by two types of circularity, serves to highlight some of the problems with that type of benchmark. The authors identify two ways in which such benchmarks can result in misleading conclusions about VEP performance. In type 1 data circularity, shown in the top right, data used to train a predictor is directly reused in its assessment. As the predictor has already seen these variants, it has an unfair advantage over those that have not. This might seem like quite an obvious point, but in the case of large meta predictors that use many other VEP scores as features, it can be extremely hard to determine exactly what data every component of the VEP has been trained with, not to mention restrictive if you have to exclude 99% of your benchmarking data set from the evaluation. Type 2 data circularity has its roots in the structure of many variant databases. TP53, for example, is a heavily studied protein with a strong relationship to cancer. As a result of this, there are many pathogenic TP53 variants in the databases that are commonly used to train VEPs. On the other hand, MYPN has hardly any known pathogenic variants. When provided with unknown variants in these proteins, a VEP that is vulnerable to type 2 circularity may assign the TP53 variant as pathogenic and the MYPN variant as benign based on its previous experience. This can lead to amazing apparent performance in these proteins or others with well-known pathogenicity or benignity associations, but poor performance in unknown or mixed outcome proteins. I also want to quickly make a distinction between VEPs that are vulnerable to these types of circularity and VEPs that are relatively immune, because it's going to be important later. VEPs that include human population data, either by training unlabeled human variants or using allele frequencies as a feature, can have their evaluation influenced by data circularity. And we've referred to these as supervised variant effect predictors in previous benchmarks. Examples include polyphen-2, meta-RNN, and REVEL. Population-free VEPs, on the other hand, we consider to be relatively immune from these influences, as they're not exposed to any labeled human variants during training. So examples would be ESM1V, EVE, and SIFT. In addition to avoiding sources of data circularity, an ideal benchmark should also be independently conducted. Of course, everyone wants to show off their sparkly new predictor in that one specific niche scenario in which it outperforms all of the competition. But if everyone claims to be the best, it ends up being very counterproductive when choosing a predictor to use. So this chart comes from a literature review which we published 2 years ago. It compares how a series of VEPs rank within the author's own internally conducted benchmark and how they're ranked in internal benchmarks of later predictors. And this really serves to highlight 3 issues of these non-independent benchmarks. So as demonstrated by this rather strikingly blue diagonal line, almost every author of a VEP finds their own novel method to be superior to all previous predictors. This wouldn't be too unusual since we do expect technology to improve over time, except for point number 2, there is a massive disagreement between benchmarks over the relative rankings of earlier VEPs. For example, the neck disease internal benchmark found that SIFT was superior to polyphen-2. However, the later Diogen-2 benchmark found that the relationship was the other way around. And point 3, SIFT, polyphen-2, and on here to a lesser degree CAD are included in a disproportionate number of these benchmarks. These are all older predictors that have probably been included because they're very well known. but it's of far more use to compare new methods to other cutting-edge VEPs. So let's take a step back and look at the benefits of using deep mutational scanning datasets as a source to independently benchmark VEPs. Clinical databases have a lot of uncertainty in label assignment. ClinVar has a huge number of variants of unknown clinical significance, many low confidence variants, or those with conflicting interpretations of pathogenicity. DMS helps us to sidestep that issue by providing actual functional evidence of variant effect. The complete independence of DMS from any previous clinical observations help to address potential training bias by decoupling functional scores from previously made observations. A huge number of mutations scored by DMS will never have been observed in any human before, meaning that no VEP can obtain an unfair advantage through them, on them. The continuous non-thresholded fitness metrics, which are produced by DMS, provide an additional opportunity to address type 2 data circularity. So in predictors that are vulnerable to type 2 circularity, all variants in a pathogenic protein may be assigned scores above a certain pathogenicity threshold. In other words, you might end up with something that looks a bit like this. But to score well against DMS, the predictor still needs to put these variants in order of fitness rather than just exceed some arbitrary threshold. And finally, DMS also provides a fair way to compare VEPs that are trained with human population data, such as ClinVar and Nomad, against those that aren't. In more traditional benchmarks, population-free VEPs can't have their performance estimates inflated by circularity and are thus at a disadvantage. The use of DMS data puts both categories onto a level playing field. Our most recent version of our benchmark takes 36 human protein DMS datasets and uses them to compare 80 different variant effect predictors and conservation metrics. So the general process of our benchmark is a single DMS dataset is selected for each of these 36 proteins, that dataset being the one with the highest median correlation to all VEPs. For every possible pair of VEPs, then, only variants that are shared between those two VEPs and the DMS data are retained. Then the Spearman's correlation between each VEP and the DMS data is calculated. The winning VEP of each pairwise comparison gets 1 point. Then across all proteins, the win rate of every VEP against every other VEP is calculated. And the final ranking, as shown in this bar chart on the right, is the average win rate of a given VEP against all other VEPs. So right now, our top ranking method is called CPT, which stands for cross-protein transfer. And I'm going to introduce a red flag right away and say that this predictor was actually trained using DMS data. We did, however, exclude its training set, along with the training set of all similar VEPs from their comparisons. The recently released alpha missense predictor comes a very close second place. And in case you're looking for SIFT, it's down here at the bottom. Not the worst predictor, we just used it as a cutoff point for the chart. I think there's about 26 other predictors underneath it. This is another way to view the results. So this heat map shows the underlying win rates of every VEP that we tested against every other VEP and used it as a basis for the final ranking, essentially just taking an average across every row. This is, however, all in terms of relative ranking and doesn't say anything about actual performance levels. It's all very well for me saying that these biases exist and that DMS-based benchmarking is the answer, but I also hope to be able to show you. So in this slide, note that population-based predictors are denoted by the brown color, while the population-free predictors are in the green color. So I'm going to use that same color scheme in future slides. This is a biased benchmark, and intentionally so. What I've done here is I've taken predictions for over 900 human proteins that have at least 10 pathogenic or likely pathogenic variants in ClinVar and 10 putatively benign variance from Nomad. I then calculated the area under the receiver operating characteristic curve for each of these VEPs in each of the 900 plus proteins and plotted the distribution of the results. We can see that as opposed to the DMS-based benchmark, where the population-based and the population-free predictors are fairly evenly distributed among the top performers, here the population-based predictors have a clear performance boost, accounting for the top 8 VEPs as ranked by median ROC AUC. Now, in this very colourful chart, we're comparing the results of the DMS-based ranking with the ROC-based ranking for the population-free VEPs only. These VEPs should not be vulnerable to data circularity, and we can see a strong correlation between the two ranking methods. I also just want to quickly clarify that the x-axis in these charts is a pairwise rank based on ROC AUC, in a similar way to how the DMS score is based on pairwise Spearman's comparisons. It just helps to compensate for missing scores, preventing VEPs from being compared in regions of proteins where one doesn't generate any predictions. Now, if we add the population-based VEPs back into the chart, the Spearman's correlation between the two analyses drops, and there's also a clear displacement of the population-based VEPs on the x-axis as their ROC-based ranking improves, but without a corresponding improvement to their DMS-based ranking. Given that population-free methods should not be vulnerable to data circularity, we can fit a curve to these points and then use displacement from this curve on the x-axis as an estimate to which the extent to which data circularity influences the ROC-based estimate of their performance. So this puts predictors like INMARF, SNPRED, and meta-RNN as some of the potentially most biased population-based predictors, at least for these datasets, while predictors like Varity, SNAP2, and Suspect remain relatively unaffected. And now it's time for me to talk about some of the larger caveats in this analysis. So the 36 DMS datasets that we've included in this analysis are a subset of 41 candidate datasets that passed our initial filters. The remaining 5 datasets were excluded because the overall correlation with all VEPs was very poor. These DMS datasets were not focused specifically on human disease, but rather on the elucidation of some biological mechanism. Not all DMS datasets are relevant to human disease, and some care has to be taken when selecting relevant ones. I mentioned earlier that our top performing VEP was trained using DMS data, and this is actually true for 5 VEPs in the benchmark. As DMS is performed on larger numbers of proteins, it becomes an increasingly attractive dataset to train novel predictors with. Our current approach is to exclude the training data of every such VEP from its own rank calculation, and to check that performance on the training data is similar to performance outside of it, which has been the case so far. But widespread adoption of DMS as a source for VEP training might necessitate other benchmarking data sources to be found in the near future. One example could be data derived from case control studies. And several VEPs that aren't directly trained using DMS data may have undergone some level of hyperparameter optimization to improve performance on it regardless. This is another way that data circularity can creep back into the assessment of VEPs using DMS data. Just like VEPs that are directly trained with DMS data, this practice is going to become more common as DMS becomes more accessible. Now, one quite interesting question which has been posed to me is, could VEPs replace DMS? After all, they're both doing the same job, and modern VEPs have managed to outperform DMS in several cases. After all, we all know that AI is already coming for our art. AI is coming for our jobs. AI is coming for Sarah Connor. What prevents DMS from being next on the AI hit list? Well, despite VEPs being easier and considerably cheaper to use, DMS still retains several big advantages. First of all, the fitness impact measured by VEPs has its roots in the biological effect of the variant, whereas tracing the logic behind a VEP interpretation of a variant can, depending on the VEP, be near impossible. This is of particular relevance in the medical field, where decisions used in patient care need to be accountable. DMS is also much more versatile than VEPs, and it can be repeated under multiple different conditions. Do you want to know the effect of 10 different drugs on variants in a protein? You can get your answer by performing 10 DMS experiments, while the VEP predictions will remain unchanged. Almost every DMS metric I've seen has some indication of prediction quality, and the remainder have already disposed of low quality results prior to providing their results publicly. Some VEPs offer something similar, but the majority just provide a score with no indication of quality or certainty. And finally, let's say I want some clarification on some P10 variants, for example, like what the likely mechanism behind their predicted pathogenicity could be. I could email the people who performed the P10 DMS, and they'd probably be happy to help and also very knowledgeable about that subject. But emailing the author of Diogen 2 or most other predictors with the same request would probably be a lot less productive. And that's it for my talk. I want to thank everyone from the Marsh Lab for their help and support and their feedback on this presentation. And I'll be happy to take any questions as long as they're the easy ones. Thank you.
Thanks a lot, Ben. A very interesting and surprising presentation, very useful. I have here some questions from Adrien. For proteins without a Sol3D structure, are population-free VEPs or population-based VEPs better at predicting pathogenicity?
So the structural question is something that we looked at with our first benchmark, it's got to be like 5 years ago now. And what we found at the time was that the inclusion of structure into the predictions actually had negligible to no effect on the quality of the predictions. However, now that we've got these big well-known predictors that include structure like alpha missense, it's definitely worth looking at again. Yeah.
Okay, thank you. And then I was thinking, is there any particular dataset, DMS dataset that you have used where all the predictors aren't able to predict the outcome?
So the 5 DMS datasets that I mentioned that were excluded were done so because the all variant effect predictors had extremely poor correlation with the DMS results. I believe one of them was NCS1, neuronal calcium sensor 1, obtained from the MaveDB website. I don't recall the identities of the other 4. But
Okay.
yes, it definitely happens.
And in the same regard, do you remember if these were DMS performed on yeast or in cell-based or any particular difference? Or
so yeah, I have looked into whether performing the experiment in yeast or performing the experiment in human cells, and what assays have an effect on whether or not the DMS correlates well with it. currently, it seems that the actual assay itself doesn't matter so much as the protein. So we have good and bad correlating yeast-based assays. We have good and bad correlating human-based assays. It seems to be very protein-based rather than assay-based. I think the NCS one might have been a yeast-based assay, if I were to take a stab at it.
Okay, I think we have some time for some other questions, so I will keep on with some of them. Cindy Lee, I'm wondering how you output predictions of PEPs on DMS data, if some are designed to output pathogenicity scores.
Could you repeat that, please?
Yeah. I'm wondering how you output predictions of BEPs on DMS data, if some are designed to output pathogenicity scores.
So what we did was we made predictions for every possible amino acid change in the proteins that the DMS was performed on. And then when we did our pairwise Spearman's comparison, we just removed predictions that weren't present for one of the two VEPs or the DMS that were being compared if one or more of them wasn't present.
Okay. Then we have Free Throat saying that was a brilliant talk. And then he's asking, have you thought about whether there are some classes of protein, maybe intrinsically disordered, where DMS may be beating BEPs for a while longer?
Yeah, intrinsic disordered proteins are quite interesting in terms of their results from VEPs. So obviously DMS is almost always going to give a valid biological answer, but in intrinsically disordered proteins, you're generally going to have more permissibility in the variants you can have there. Which, sorry, I've lost my train of thought.
We also have those questions in the Q&A that you could answer after, just to let you know.
Yeah. Okay. Thanks again, Ben, for your wonderful talk.